Um, I'd like to use this example of physics. And there's used to be electric force and the magnetic force separate. Remember those time period back then? Then someone with a long beard combined this thing brilliantly, right? Brilliantly. Who did that? I guess Maxwell combine this observation of Faraday, whatever, electric force and magnetic force can be explained in same paradigm, mathematical paradigm. All right? So in physics, forces are explained with a principle. Right? That's very intuitive notion, but sometimes when you go down to this difficult level, it's beyond our level of comprehension. So there's a mathematical ideas written down. It's very difficult to feel the intuition physically. So that's the level we are entering here. There's no more physical intuition. It's just mathematics right there. If you have algebraic intuition, then you begin to accept this mathematical framework. So he discovered the mathematical framework. This electric force and magnetic force is playing together in one mathematical paradigm. Okay, so that was a great moment. And then later, there's something called weak force. It's inside the particle level, right? There's weak force. And these two things are finally put in together wonderfully around 1970. This is called Standard Model. And they got a Nobel Prize for this. This is a mathematical paradigm in this one. It's called the Lie algebra. So they use Lie algebra to combine this difficult phenomenon they see from observation and empirical data. It's called the Standard Model. Is that something you can't read? Standard Model and weak force. Okay. They put this under this very abstract algebra. Lie algebra, people who invented Lie algebra had no idea what's going on in physics. It's just pure mathematical daydreaming of envisioning. And they use that to combine these two things happening in the same mathematical paradigm, just like that. In this level, there's no physical intuition. You can't understand force acting on that, and then therefore, that classical mechanical way of understanding how the forces interacting each other is not possible in here. They just found one mathematical paradigm to explain the whole thing. And it was Einstein's dream and everyone else's, maybe Stephen Hawking's dream, to find one mathematical paradigm that put all the 5 different forces in one, explained by one mathematical framework, right? That is the unified field theory of something like that. So that's happening in science. The big driving force of in physics, right? You hear all the time for Ben Green and all the other people who are contributing to, let this thing known to a public. And here's the mathematical side. Back then, of course, the mathematics and physics, they're all the same thing. They're the same people, right? But at some point, mathematics got more sophisticated. They realized that this is their own profession. They don't have time to both. That's not really the reason. But they just pursued their own direction. Around 1800, they realized that our mind itself is a world. That's where mathematics is heading. So, but what we are doing here is a complex number. So I made a nice analogy of the complex number. So mathematics, one sophisticated idea in mathematics in your education is functions. So you early on learn function, but I claim that really understanding what a function is takes a long time. But you get used to it early on. So here's some famous exponential transcendental function. The transcendental word comes from the situation it's very difficult to compute those values. e to the x is important exponential function. Values are usually transcendental numbers. And there's some other important function, right? It's called trigonometric function and sine and cosine. This is also transcendental function. It's easy to understand geometrically, but very difficult to calculate numerically. So all of these functions you have to completely rely on calculator to handle the values, right? So those are difficult functions. Many of students in mathematics education just blindly just accept it and never think about it. It's that hard actually, right? Now, there's this invention of complex numbers. Very innocent start They had no idea what this is leading into. They just invented these complex numbers because we want a number system to deal with in a situation where the quadratic equation is not solvable. Things like that. Very, very simple idea. Back in that Greek period, it started early on. But they realized that this very innocent system of this thing, these two things, if you look at the definition of e to the x and sine x, cosine x, has nothing to do with each other. That's really true. But in a complex system, these two completely different thing is explained on the same number system. There is a link between these two things. All right. If you have studied the hyperbolic function in calculus, it's derivative phenomenon of hyperbolic function which is made out of e to the x. So a lot like sine and cosine x. Derivative of sine hyperbolic is a lot like sine x, derivative of sine x. Behave just like that. It's a good indication why there are some connections between that. The behavior of the derivative. But its invention of complex numbers actually put these two different phenomena together and explain it as the same phenomenon. So there is this two different types of elementary function, which is not polynomial. Polynomial is easy. It's add and subtract and multiply and divide. These are different. These two things became one function because of a complex numbers. This is done by Euler. Many people in YouTube read this Euler or something. As far as I know, Euler is a correct pronunciation. Brilliant mathematician. He just put these two things together. To me, this earth-shattering moment. If you look at that equation, which is in the section 1, is this most amazing. As far as I know, the a majority of mathematicians voted to that result. This is the most beautiful result in mathematics. How these two things combine together. All right. The sine x and the cosine x is used as a wave function, right? Quantum mechanics, all the waves are represented using the sine of and cosine x. And this involves, frequencies. If you decompose in a spectral decomposition, and then you have pure waves coming out of this some complicated wave. So frequency and amplitude, and those are what's involved in there. So again, out there in engineering and science, they have to analyze these waves. It's a fundamental part of the physics. It is governed by these two things, the frequency and amplitude. And if you just play with the e to the sine x and cosine x, the mechanics of these waves, which is quantum mechanics, is algebra, is unthinkably so complicated. But because of this complex number putting together one system, the interaction of this one become a lot neater algebraically. And that's the right word to put it in there, right? So that's the accomplishment of the invention of a complex number. And it's so interesting that it started very innocent. Let I squared be a number whose square is -1. It's a simple start, gives a lot of surprises. It's the first big surprise. All right? And more mathematical application surprises the following. So this is item number 1 that I would like to advertise about how awesome this complex number is going to be. Second one is this polynomial, for example, x squared plus x plus 1 equals 0. This does not have real solution, but if you apply quadratic formula and you have something negative in the square root, right? So let's extend our number system from real number to something called a complex number, which is denoted by this boldface C. This is boldface R, representing a set of all real numbers, number line. And boldface C is a complex number. I haven't introduced yet, but we extend the number system. You keep R, and we have a new kind of number. Then you can explain kind of solutions of that. It's quite nonsense. It's very difficult. It took a long time to accept mathematicians as actual number. So that's what happened. Just to take care of what kind of polynomial? Polynomial of degree 2, right? Now, What about polynomial degree 3? And what about polynomial degree 5? And what about polynomial degree 2014? Do we still have to invent another bigger and bigger numbers, right? So they took care of degree 3 and degree 4. Some people, ancient people, worked really hard, and just with that complex number, they found the solution of degree 3 polynomial in degree 4. And degree 5, they got stuck. They couldn't do it. Everybody tried. There was no formula using this extended number system complex, and they couldn't find a formula. And some French guy, his name is Abel, and he proved that, basically, that there's no formula. We do not have a notation that describes a solution. But surprising thing happened is that mathematicians could show that we cannot write down the solution neatly, but we can prove that, and all the degree 5 polynomial has a solution in C. That complex number has a solution in that, but we do not have a notation for that. So let me give you an example of this, what I just meant by notation. X to the 5th plus x plus 1 equals 0. This is a degree 5 polynomial. If you sketch that polynomial, it looks something like this. It's not straight line, but does not have much of a curvature. Just keep going up. And just right there is number. Right? You can kind of see that using Mathematica. There is a real number there. Okay? And what I'm saying is that it crosses right there, and this guy, Abel, proved that we do not have a notation to describe this one. But there's there. We have a notation for square root 2, right? We use the square root 2 symbol. It's a symbol, right? And if you use a, calculator, you can write down some decimal numbers, but that's not exactly what square root 2 is. So we use this notation, right? He was saying we're out of notation as you enter degree 5 and higher. But you can see clearly there's this number right there. That's what I mean by there is a solution in complex numbers. Okay? No matter what degree of a polynomial you write it down, if you don't see the real numbers, if you enter this complex number, there is a solution. But you don't have a notation for that. So that's called fundamental theorem of algebra. All the polynomial has a solution in C. So you don't have to invent no more. C is it. We just invented one number, I, to take care of quadratic polynomial. But what happened? It took care of all the degrees. That was a huge surprise to mathematicians. They began to sense it early on. Gauss tried it, Legendre tried it, the famous Euler tried it, everybody failed. Nobody proved it in 1806. That was the first time a rigorous proof is given. But it was that hard. Anyway, it's done now. Every degree of a polynomial has a solution in the C. No more invention is necessary to take care of a polynomial. Another surprise you will see in this course is that this is nonsense. You know that, right? Sine x is not going to be 2. And we make sense out of sine x in a complex number, and this happens. Everything you write down, pretty much it has a solution in a complex number. This makes no sense. You know why this makes no sense? Sine x being 2. In real numbers, sine x is not going to exceed 1 or below negative 1. It is in between 1 and negative 1, right? This will never happen. But we'll define this function in extended number system, and this guy happens. All right? That's why we're entering something that defies our visualization. Algebraically, so simple. I will be giving a talk in November about the work of two Fields medalists. Right now in Seoul in South Korea, the International Congress of Mathematicians is taking place. It's a 4-year event. It's the most important event for mathematicians. They announce these awards to young mathematicians, which is equivalent to Nobel Prize in mathematics. Believe it or not, there is no awards given to mathematician in Nobel Prize. So this is substitute. that. But one of the work is about this something called the Riemann surface that we're not going to get into in this course to Riemann surface. But it is an extension of this course, the next level, and her work is about this Riemann surface, so I'll invite you to come to that talk. But it's going to be in November. And from there, after they establish these complex number and get these two surprises, complex number putting these two transcendental functions together, and all the polynomials taken care of is all in there, right? Plus, we're entering this Riemann surface. This is amazing world that they enter. These three things is just manifest and how brilliant this invention, how surprising this complex number became. It's really shocking to me if you look at the history and how it started and what it did is just amazing. And since that 1800 and on, this Riemann surface kind of dominates 90% of the higher mathematics. The phenomenon is coming out as Riemann surface dominated 90% of the higher mathematics, and since 1800 on. So it's that of importance.